Yeah, here is an example for retention time and partition coefficient. The question is, methane gave a sharp peak spike in 42 seconds, whereas benzene required 251 seconds. The open tubular chromatography column has an inner diameter of 250 micrometer and is coated on the inside with a layer of stationary phase. Okay, the figure is like that, right? This one, this column wall, and inside wall is coated with stationary phase. Usually, it's a liquid, right? And its thickness is 1 micrometer. Okay, and question is, estimate the partition coefficient for benzene between stationary and mobile phases and state what fraction of time benzene spends in the mobile phase. Wow, the question is looks quite difficult. Okay, but let's consider one by one. This is a usual case. This is a capillary column. Okay, and capillary column is made of silica or other materials, and in length is quite long, sometimes more than let's say more than 100 meters. Okay, anyway, it is a thin tubular column, yeah, and the inner diameter is 250 micrometers. Okay, but since 1 micrometer, the thickness is of that's for the stationary phase. So this diameter becomes smaller by 2 micrometers. Okay, here's one and there's one. Okay, so inner diameter is 248 micrometer. Okay, then the cross-sectional area of the column is pi r1 squared. Okay, and the inner diameter is the half of this one. Okay, half of the radius, 124 micrometers. Okay, so the cross-sectional uh, area of column is that 4.83 times 10 to 4 square micrometer. Okay, and cross-sectional area of coating, yeah, cross-sectional area of coating, this one, yeah, cross-sectional, and is 2 pi 2. So you have to first calculate the perimeter, yeah, and thickness. Okay, 2 pi r2, yeah, and you have to take the average. Let's take the average, yeah, uh, which is the average here. Uh, this the diameter from here to the inner part is 124, and this is here. The inside part is 125. So the average is 124.5. Okay, so 2 pi multiplied by this number is perimeter and the thickness. Okay, and then that gives an area of the cross sectional section of the column of the liquid phase, and it gives 7.8 times 10 to the 2 square micrometer. Okay, and since you have to calculate, let me see the volume ratio here, Vs divide Vs to Vm is what? Since the length is the same, yeah, so we don't consider the column length, only consider the area. Okay, Vs is what? This one. Okay, the volume of stationary phase. Yeah? Now we calculated uh, the area. Okay, which is this one, and the volume of mobile phase is inside the area, which is this number. Okay, and then the ratio Vs to Vm is 0.0161, and by definition K, the capacity factor is Tr is what? Tr is 251 TM is that's for benzene, the methane, okay? Methane, it doesn't retain in the column is 42, okay, and divided by 42, and which is 5.0. That is a retention factor or capacity factor for benzene, and the K also expressed is by this one, and this is 5 equals K. That's a partition coefficient, and we just we obtained this one, the value, the volume ratio, and here we get the partition coefficient, the benzene between the stationary and mobile phase, which is 310. That is a partition coefficient. Okay? And here, K also, yeah, we can write it this way. Okay, and which is TR minus 0. Yeah, this one, and that is a TS. Divided by TM. Let me see. And TS is K T multiplied by Tm. Okay, so the fraction of time in mobile phase is what? Fraction of time in mobile phase is given by this one. Ts plus Tm, Tm over Ts plus Tm. Yeah, and here Ts is this one, K multiplied by Tm. Yeah, and then we get this number 0.17. Okay, that's the fraction of time in mobile phase, because this is one of the questions. Okay, fraction of time benzene spent in mobile phase. Okay, this one. And what is the other fraction? 0.83. Yeah, that fraction is for that's the fraction of time benzene spent in the stationary phase. Okay, yeah, it is not that difficult. Okay, so as long as you know the definition, okay, of these terms, it is rather easy to calculate. Okay, here is the retention volume. Yeah, we define the retention volume. Yeah, retention volume VR is the volume of a mobile phase required to elute a particular solute from the column. Right. Now you read carefully. VR is retention volume. Okay, volume of the mobile phase required to elute the particular solute. Okay. So VR equals TR. TR is the retention time for a particular solute, and UV is the volume flow rate. Okay, yeah. The equation is given by this one, and here, since K is given by this equation, and then it is expressed by this one. Retention volume VR minus Vm. Vm is also retention volume for what? A non-retained solute. In our previous example, M is methane. Okay, divided by Vm. Okay, that is another calculation for this capacity factor. Okay, and now consider scaling up. What's the scaling up? For the analytical purpose, you don't have to scale up the system. Yeah? For the only analysis purpose, okay, you inject a very small amount of your analyte, okay, your mixture, and then now the small amount now pass through the column, and then we detect. Yeah? That's enough for the analytical purpose only. Okay, but there is a case that you need a lot of amount. Okay, a lot of amount. Now you have a lot of mixture. Yeah, your analyte volume is very large, and then it contains large amount of the solute A, B, C, and D, and the like. Okay, and you want to separate those solute and keep it. Okay, in that case, the same principle is applied. But the scale must be uh, much larger. Okay, and that is a scaling up. So um, the preparative purpose, using a fatal column to purify a significant quantity of a mixture. Okay, look at this figure. You see this column is my chromatographic column. Yeah, this is man who is working on the this instrument. You see, this column is really big. Okay, why big? Uh, because you want to deal with large amount of what, a mixture. Okay, mixture contains a large amount of solutes, and then you want to just separate them, right? In that case, you have to scale up. You have to scale the chromatography up quite a bit. Okay, yeah. Why do you need a large volume? Yeah, yeah, for the purpose of selling, right? If you want to separate a large volume, and then you can sell, that the component, for example, pharmaceutical and pharmaceutical industry and optical isomer drug, yeah, and then you want to what acquire a large amount of the solute, okay, for the processing or for the selling purpose. Okay, in that case, you have to scale up. You know, so we call it preparative. For example, liquid chromatograph. Okay, and prep LC. And usually scale is very large. Well, the most straightforward way to scale up is to maintain same column length. Okay, column length is the same, and then what? You have to increase the column diameter. Okay, to maintain the same column length, and to increase cross-sectional area to maintain a constant ratio of sample mass to column volume. Okay, and to maintain constant linear flow rate. That's the one way. Yeah, column length is the same, but you have to deal with a large quantity, so you have to increase the column size. Okay, if you have developed a procedure to separate 2 milligrams of mixture on a column with a diameter of 1.0 centimeter, okay, what size column should you use to separate 20 milligrams of the mixture? Okay, the uh, the column length is the same. Okay, but when you don't have a large, large size column, yeah, with the small size column, mm, you can separate. Okay, only 2 milligrams of a mixture. Yeah, to separate the 20 milligrams, you have to run 10 times. Okay, run after run after run after. Okay, 10 times to get the 20 milligrams of mixture, to separate the 20 milligrams of a mixture. But if you increase the column size, and then one run is enough, and let's calculate. Okay? Here is a scaling equation: large mass divided by small mass, okay, is large column radius divided by small column radius and squared. Why? Yeah, the uh, column area, the mass proportional to column area. Actually, the mass proportional to the the column volume. But since column, what, the distance column length is the same. So this ratio of mass is proportional to the area ratio squared. Okay, this is important. Squared. Okay, 20 milligram divided by 2 milligrams is what? Small column size is already given here. Let's see where is given here. Yeah, it is 0.5 centimeters. That's diameter. Okay, so you want to calculate the large column radius. Okay, radius or diameter, maybe diameter radius here. And then we solve this one. Okay, and then you got large column radius is 1.58 centimeters. Okay, about 3 times, a little bit more than 3 times larger. Okay, as I said, this one always true. So to separate 10 times more quantity, you have to increase your column radius by how many times? A little bit more than 3 times. Okay, this is a more effective way to increase column size. Okay. Let's temporarily stop here.